In this lesson, we're going to learn the central limit theorem and the distribution of use central limit theorem to decide the distribution of sample average, sample mean, and the summation of random variables. This has very important applications in many of the statistical procedures. And we will also apply this the result to the Bernoulli situation, in which we will observe just the count for two categories. And when we consider cumulative account for the two categories, we actually would be dealing with the binomial distributions. The binomial and the Bernoulli are the distributions that we will encounter pretty often when we want to estimate a proportion in the population. First, let's go over the definition of the i.i.d. random variable or random sample. When we have some parameter of interest, we need to estimate that. Generally, we always need to collect multiple samples from the same population having that parameter. And these multiple samples need to be identically distributed from the same distribution, and they need to be independent. So if we have x1 through xn, these are the ones that's denoted for the data from the experiment, and these are independent, identically sampled from the same distribution, then we say this is a random sample from that population. Random sample is used often because since the data are independent, different samples, they provide more information to estimating population quantity. When we try to consider using these samples to study population parameters, i.i.d. or this random sample quite often is assumed, but in some cases it's not reasonable to do so. So in that case, you have to be careful. But quite often, this random sample, like assuming the data is a random sample, quite often is a very reasonable assumption or very reasonable model to proceed. But it does not apply to all situations. Here are two examples that we think the random sample would work. One example is consider a random game of tossing coins 1 million times. And you are using the same coin and record whether the head shows up on top or tail shows up on top. So in this case, each one of we can think of flipping a coin as one trial. Each trial, it has either the head or tail, these two scenarios. And then what you are going to have, like observing the head or tail, this chance from one trial to the next trial are not really affected or changed, because the proportion of times that the head could appear really is determined by the coin itself. And if the flippings are identical, then we would expect those proportion of times the head appear, or probability that head would appear in each trial to be identical. So this is the one example of identically distributed i.i.d. trials. So description says 1 million of the coin flips. And generally, when I say we observed, for example, 500,000 of those to have head. Even though you only saw two numbers, the 1 million and the 500,000, but what's behind of that, you can think of each toss as xi. The result of each toss is xi. Xi takes value 1 when it's a head, or 0 when you see a tail on top. So that's one example. The next example, in a random poll of 900 likely voters, record whether an individual would vote for candidate A. So again, if you think about what is the recorded number out of this experiment or out of this whatever study, you're going to see just a number, 900 likely voters, and then you might see, for example, like 480 of them vote for candidate A. You only saw two numbers, but these 480 are really a tabulation of each individual person's vote, whether that person votes for A or not voting for A. If the person votes for A, we can use like an X variable to be equal to 1 to record that person vote for A. Okay, and the 900 voters, you have X1, X2 up to X900. Each one of them is either 1 or 0, but one particular person take 1 or 0, that's not something that we know. It's a random number that might change from person to person. So that's examples of i.i.d. random variables. As we already know, different samples would have different values. Therefore, these variables would change value. So they are referred as random variables rather than just variables. And if random variables are identically distributed, they should have the same mean, same standard deviation, and also many other attributes that we did not mention. For example, if we think about the skewness, they would also have the same skewness. Okay. If we have a collection of the random variables x1 through xn from a population, and they have the same variance mean, variance sigma squared, and standard deviation. If we have these being i.i.d. or being a random sample, that's the same meaning, and we would always have all of these having identical mean, identical standard deviation, identical variance. And the mean is also referred as the expectation of the random variable. We will use the expectation or the mean interchangeably, but expected value simply is referring to the long-term average of possible values weighted by their probability. These mean, variance, and standard deviation, they are all population parameters that's inherent with the population distribution. And when you have a sample collected, you also have the average from the sample and the sample standard deviation from the sample or the sample variance from the sample. Those will change from one data collection to the next data collection. So these are sample quantities. They are not population parameters. Samples are observed from a population, as we already know. They change from one sample to the next sample. Like for example, consider the battery life of iPhone 7. That supposedly has normal distribution with mean of 6.5, standard deviation of 2.872 years. And this statement is giving a population about all the batteries of iPhone 7. And the mean, if you consider all possible iPhone 7s together, the lifetime of those batteries is 6.5. That include the batteries that have already been used and also the batteries that have not been used. So those are hypothetical ones. And this next one saying 3 iPhone 7 customers are reported their batteries stopped holding charges after a certain time. And the customer one's battery lasted 8 years, second one lasted 5.5 years, and so on. These are simply just the sample values, and they are a realization of the actual random variable. And for these values, if you take another sample of 3 customers, then their values would be different. So if we compute the average from these 3 batteries, it will be one value. Like this example, the average of 8, 5.5, and the 4 is 6. That 6 is different from the population mean of 6.5. You cannot expect the average from the sample to be identical to the population mean. Instead, we'll just try to use the sample mean to estimate the population mean, but there is a difference there. Similarly, the sample standard deviation, if we compute it from this example with 3 samples, 3 customers, it would give a standard deviation of 1.51. And we are using that sample standard deviation to estimate a population standard deviation of 2.8. So in this case, with a sample size of 3, you can see the difference is pretty big, 1.5 versus 2.87. So in general, when we consider these samples and we compute the averages, we know it's different from one sample to the next sample, and that will lead to the averages to be different. So here is just a simulation experiment to generate samples of size 3. So instead of just one sample of 3 customers observed, here I actually generated the data from computer as if I have 1,000 sets of customers. Each set contains 3 customers, their iPhone 7's battery life. The first sample contains 3 values, 2 to 2, and then that will give me the average of 2, and so on. In this example, what I'm considering is that like the population consists of just 10 values from 2 years, 3 years, up to 11 years. So with those 10 possible values, and if you consider any of the one customer's iPhone, then this value would be one of those 10 numbers. So when I generate one sample, I'm just taking one sample value out of those 10 numbers for that customer. And if I have 3 customers, then take 3 values out of each one out of these 10. So that gives me these different possible scenarios of generating the samples for 3 customers. In this case, in fact, since there are only 10 possible values, each customer's phone battery could be just one of those 10 numbers. And if I have 3 customers being sampled, each one has 10 possibilities. Total would be total 10 times 10 times 10. That's many ways of having different values for the set of 3 customers. For each set each of the sample with I'm sorry, it's not a set, it's really a sample that contains those 3 values. For each one of them, we'll calculate the average, and that last column in this table give us the average lifetime from a customer or a set from a sample with 3 customers. These values basically give us the possible values of the average if we consider the experiment being conducted many times, and each one of them will result in the different observed xi's and therefore different averages. So we can plot a histogram of these averages to see how the distribution of the average look like. The right-hand side, this plot gives us the histogram. You can see in this example, we started with 10 values, and after we're taking the average, they're still within similar range, but what will happen is the distribution becomes like a bell-shaped instead of just taking those 10 numbers. Originally, it's just integer 10 numbers. And this histogram has mean of 6.5 and standard deviation of 1.659. What if the sample size is 9 instead of 3? So in that case, we have 9 customers, and each customer is the iPhone's battery life is one of those 10 numbers. So if we put 9 customers there, we would have each customer has possibly 10 of those values. And if we put the total, consider all possible scenarios of these 10 customers, 9 customers battery life, put all of them together, we would have 10 for the first customer, 10 possibility for the second customer, and so on, and 10 possibility for the 9th customer. Altogether, it's going to be 10 to the power of 9. That's way too many of them. And here again, I just randomly selected 1,000 of those and calculated the average from the 9 customers' battery. The last column in the table shows the average from these 9 of them. And you see that these values are, this time, they are smaller. They no longer goes from 2 to 11. Instead, most of them are 6, 7, or 5 something. And the histogram on the right-hand side also shows that the range now is smaller. It's about from 3 to 9 something. And if we look at the average from all these 1,000 of the averages, it gives 6.48. And the standard deviation is the 0.96. Go back to the data. Okay, we don't really know what is the true mean, what is the standard deviation either. But what we want is to estimate the mean of the battery life for the iPhone 7. So we will, but in reality, what you're going to have is just one row of the data. That's one sample, one row of the data. And if you compute the average, you're going to get only one of these average. For example, if your data happen to be this row, and then you computed the average would be this much. And that's the one that you're going to use that to estimate the population mean that you do not know. So in order to do that, to use that number to estimate the population mean, we really need to know the behavior of this X bar in order to give us a good idea of how good is the estimate. So this next part, we're basically trying to see what is the distribution of X bar when we don't have all these different rows observed. Here is for the same iPhone 7 example, if instead of 9 customers, suppose we consider 25 customers, 36 customers, and so on, then what will happen to the sample mean? The first one here, this is for the sample size of 25. You see that the range shrinks even further. Now this is shortly, it's just above 4. And this one is above 8. So roughly about, let's see, between 4.3 to 8.3. So that's for sample size of 25. We take the average of those 25 numbers. And these averages will range between around 4.3 to 8.3. And the distribution again looks like a bell-shaped normal. And the next one increased the sample size to 36 rather than the 9 or 25. So we take the average for each of the samples, and again, we look at how the possible values show up in the histogram. You can see now the lower bound is around 5, upper bound is about like 8.1. So it shrinks even further, but still the distribution is centered around a similar place. This is the center, and here's the center. It's centered around a similar place, but the spread reduces. When we have sample size of 49, it also shrinks further. And similarly, sample size of 64, it gets even smaller. Sample size of 100 and sample size of 400. As we increase the sample size, the center seems to stay where it is. And that center, in fact, is the actual population mean. These averages we computed from the sample, they are centered at this population mean, and the variation reduces as the sample size increase. So the mean and standard deviation of averages, how actually it behaves. This is a tabulate of the different sample size and the averages from the samples and also the standard deviation. So this is the average from the 1,000 samples out of the experiment, 6.5, 6.54, and so on. So in general, averages, they tend to be out of the 1,000 samples with that specified sample size. So this is from 1,000 samples, okay? 1,000 samples. And the computed average from each sample. So you have really 1,000 averages. And here is the average from the 1,000 X bars. And this is the standard deviation of the 1,000 X bars. Okay. So the average from the 1,000 averages, they all seems to be around the similar value mu 6.5. And then the standard deviation of these 1,000 averages, if we have just 3, the sample size of 3, this is 1.65. And if we have a sample size of 9, it becomes 0.942. And as we increase, these standard deviations of average shrinks, become smaller and smaller. And the population standard deviation is the 2.872. And now let's see these standard deviations. The last column gives the sigma over square root of n. If you look at it, this column, the last column here, compared to the previous column, they seems to be pretty close. Okay, so that tells that standard deviation of x bar is actually around the sigma over square root of n. This is particularly the case if the sample size n gets large. Like n equals 400, n equals like 100, and so on. So that's the standard deviation and the mean center of the sample mean. So this basically states what we just discussed. The distribution of x bar, okay, this is talking about the distribution of x bar when you have one sample collected and then you calculate the x bar, and you have a next sample collected, you have x bar computed again. And when you consider all possible such samples collected and each one of them you calculate x bar, then in the end what you get, the possible values of those x bar gives the sampling distribution of x bar. And let's say the sampling of distribution of x bar is centered at a value, and this value that's denoted with mu and the subscript of x bar. This is just the center of that distribution. And the standard deviation, we use the sigma with the subscript x bar again. And these two quantities, they are related to the population mean and the population standard deviation. And the relationship is given in the formula below. X bar, its mean is really equal to the population mean of each of the xi. So the mean of x bar is the same as the mean of xi. And the standard deviation of x bar is equal to the population standard deviation of the xi's divided by the square root of n. And this quantity, sigma over square root of n, is referred as the standard error of x bar. Okay. So that's the mean and standard deviations. And in fact, we know more than just standard deviation and mean. If the sample size n is large, and what we have, these xi's are a random sample, and if the sample size n is large, what we could say is that the sampling distribution of x bar is going to be approximately normal, and the mean is equal to the mu, and standard deviation is equal to sigma squared. Sorry, the mean is normal. I'm sorry. It's normal distribution with the mean equal to this mu, and the standard deviation equal to the sigma over square root of n. So that's if n is large. On the other hand, if the n is not large, in that case, we need to make additional assumption that assume that the population distribution is normal. If the population distribution is normal, in that case, population is normal. In that case, the sampling distribution of average will be exactly normal, regardless of how big is the sample size. Whether you have sample size of 1, sample size of 2 or 3, and so on, the average would always be normally distributed and has the same mean and standard deviation sigma over square root of n. The mean and the standard deviations, this one does not depend on the, does not. This one, okay. This is a fixed value. These are fixed values that do not depend on the distribution. Do not depend on the distribution of the population. Okay, so that's this central limit theorem. Basically, what that central limit theorem say is that if the sample size is large, we can basically use the normal distribution to compute any probabilities related to the X bar. Similarly, we can also use the normal distribution to consider percentiles related to the X bar. And this result is always is for large n case. In practice, we only have a finite sample size n. If a finite sample size, then we use this approximation. The approximation may or may not do well depending on how is the population distribution look like. If the population distribution is very skewed, like for example, here is the population distribution is highly skewed. So you have some large values on the right-hand side or on the left-hand side. In that case, we will need n to be very large. So this is a PDF of the xi, and then the PDF of x bar will be still approximately symmetric when the n is large. So if n is very large, the PDF of x bar will look like symmetric. Okay, so that's even if the population is skewed. But if the population is symmetric, in that case, you do not need n to be very large. Like the iPhone battery example, in that one, if we try to consider what's the population distribution, each of the battery life is equally likely to be one of the 10 numbers. So that one is actually uniformly distributed on the 10 numbers. When it's uniform, it's not really skewed. So the average from those uniform numbers will be pretty symmetric very quickly, even for small n. Here is just some of these histograms to help you to see how the sample size changes. As the sample size change, how's the histogram going to change? Histogram of the sampling distribution of X bar. So for the sample size of 1, that's basically this histogram is like the population distribution. This is like the population distribution. And this one is average from, so this one is the average of like x1, x2, and x3, because sample size is 3. And this is talking about the from 1,000 samples. Each sample we have an average, so you have 1,000. These two are 1,000 averages, X bars. And these 1,000 averages, we plot this histogram, okay? And with sample size of 3, as you see, when the population is skewed, sample size of 3 taking the average, that distribution is also skewed. When we change the sample size to 9, so which means we're going to have x1 through x9, we calculate the average. And suppose you have the sample size of 9, this experiment 1,000 times taking averages, you calculate the averages for each sample, and then you plot the histogram. This one is a little bit more centered, so more centered than with sample size of 3. Here on the horizontal axis, you need to see that I did not use the same scale. This upper value is 40, around 40. But here, this part upper value is around like about maybe 28. So the values are shrinking. I mean, in terms of positive values for the average, when the sample size is getting larger, this positive values of the average is shrinking. So if you look down further, like 25, 36, and 49, these values will become smaller and smaller as we take values of 400, sample size of 400. This time, the upper positive values is like the 18. Okay, and lower positive values is about 14.5. So this basically shows that the same thing that we have mentioned earlier. As the sample size increases, the sampling distribution of X bar will become more and more symmetric and centered around its mean, the mean of the population. Okay. So this is that central limit theorem, just showing you with the simulation. How large do we need the n to be? A general rule of thumb, mostly people just use 30 as the cutoff. Our textbook, the divorce textbook, use n equals 40. So if it's n equals 40, they suggest use the central limit theorem. But the reality is that you would better check whether the population distribution is very skewed or not. If these observed data are very skewed, in that case, the sample size of 30 is still possibly not enough. And you would hope you would much larger n would give a better approximation in terms of distribution of the X bar. But if the X bar distribution of X bar is not highly skewed, then the sample size 30 is fine. You can use even smaller than that if X bar, if the observed data Xi distribution is symmetric. The sample size does not even need 30 for X bar to behave approximately normal. Let's look at an example. This is a blood pressure measurement. Blood pressure measurement generally has variations throughout the day, and if a patient's systolic blood pressure is supposedly it's normally distributed with mean 160 and the standard deviation of 20. So this is the population. Population quantity have the mean of 160 and the sigma is 20. And we want the sampling distribution of the following. A is a single blood pressure measurement. If it's a single, then this A with the distribution would be just the same as in the population. This is the normal, and the mean is 160 and standard deviation is 20. The next one, B, average of 3 measurements taken at various times. For 3 measurements, this is n equals 3, and we are looking at the sampling distribution of the average of 3. So it's talking about the X bar from the 3 measurements. For this one, we know that if population is normal, then the average is always normal regardless of what is the sample size. So we can safely put this normal for all 3 scenarios. The mean in all situations would also be the same as the population mean, 160. Standard deviation will be different. It will be population standard deviation, population sigma divided by square root of sample size. Similarly, when we have 5 measurements taking the average, standard deviation will be sigma over square root of 5. This is because the population distribution is normal. Distribution is normal. Okay. Next example, suppose now if a systolic blood pressure exceeds 150, then the person would be considered a high blood pressure and need medication. What is the probability that the single blood pressure measurement will fail to detect that the person has blood pressure? So for this question, greater than 150, then that's a correct measurement, right? If one measurement and we find that it's greater than 150, then it will say that this person needs a prescription. So fail to detect would mean that the measurement X is going to be less than 150. So basically, we're trying to see what is the probability of this one. So probability of X less than 150. For this example, we already know the blood pressure X has normal distribution with mean of 160 and variance of 20 square. So in this case, we can compute this probability with just the p norm. And we put in the 150, that's the one we want to compute for probability. We put the mean of this distribution and we put a standard deviation there. That will give us the probability. So for this one, after finished computation, you will see the value is around 0.3. The next one here, 5 blood pressure measurements are taken at various times. And what's the probability that the average of the 5 will be less than 150? For this one, we're looking at the average from 3 measurements. And again, we want to look at X bar less than 150. So for this case, we know X bar has a mean equal to 160 and the SD equal to the 20 over square root of 3. So this probability will be computed with the P norm, and we put the 150 here and the center 160, and standard deviation is 20 over the square root of 3. After computation, you'll see this probability around 0.13. Next one, how many measurements would be required in a given day so that there's at most 1% of probability of failing to detect the high blood pressure? So this is saying that 1%, 0.01 is the probability of X bar less than 150. So that's the probability. We know this probability is less equal to, okay, it's not equal, it's less equal to. So probability is less equal to 0.01. If we know the distribution of X bar, we use the P norm to compute, but here we do not know the distribution of X bar. Even though we know it's normal distribution, but because we don't have the N here, so we do not know the standard deviation. Therefore, this question is basically trying to consider for the right-hand side here, X bar has the normal with the mean of mu and standard deviation equals 20 over square root of N. This X bar, using that distribution, we know the probability of less than 150 is 0.01. This basically says that 150 is the 99th percentile of this distribution. So if 150 is that 99th percentile, then we can use the percentile to help us compute the sample size. Okay, so percentile that we will, okay, this is the first one, the part 1 using one measurement about 0.3. And here is the answer for the second question is about 0.13. And then for the third question, we know that this 150 is the percentile, and the percentile from the X bar is related to the percentile from the standard normal, the Z-score. So if we convert X bar to the Z-score, like this one, X bar minus 160 over 20 divided by square root of N, this has a percentile easily obtained from R or from the table. So this would have a, let's say, 99th percentile given by 150 minus 160 over the 20 over square root of N. So the 99th percentile is equal to that. And in other words, this part, this is the square root of N. This is equal to 99th percentile. And for 99th percentile of the standard normal, we can get it with the Q norm of 0.01. That'll give us the value negative 2.326. And from here, we can solve for the N. And that tells that N has to be at least 21.64. in that case, we're going to take n to be 22, always round up in order to guarantee this inequality. So we need 22 measurements in order to have at most 1% of chance to fail to detect high blood pressure. So summarize for this part C, what we need to realize is that when we say that at most 1% fail to detect that, this 1% is the probability of X bar less than 150. And therefore, 150 is the 99th percentile. And for that 99th percentile, we need to relate to the standard normal's percentile because distribution of X bar depends on the unknown standard deviation, which is sigma over square root of n, but we don't have that square root of n. But once we convert it to this standard normal z, then the percentile of the z becomes the 150 minus 160 over the standard deviation. And the z has percentile that we can easily obtain without relying on anything unknown. So making the two percentiles equal would allow us to solve for the unknown n. The next example, this is about the engine power. We are looking at the speedboats made by Ford, and the mean power is 220, and standard deviation is 16. And assume we have normal distribution. So this is giving us the population. Here is the mu. Oh, this one, mu is equal to 220. And here is the standard deviation, sigma, 16. And we have this normal distribution, that's the population. A potential buyer intends to take a sample of 4 engines. So this is a sample size of 4. And this buyer will try to consider 4 engines and look at the average the engine power to. If it's less than 215, then this buyer will not place an order. So in this case, what's the chance that this buyer will not place an order? Is basically computing what's the chance of average from the 4 is less than 215. So population distribution, we already know it's normal. And since we have average, the average X bar has a normal distribution with the mean of the equal to 220 and standard deviation is sigma over square root of the sample size, that will be 8. Therefore, we use the normal distribution here, 220 as the mean, 8 as the standard deviation to compute the probability. After computing, you see the answer is 0.2659. So basically about 26.6% of the chance that the buyer will not make an order. Now, what if the customer is able to sample 100 engines and check their power? And what's the chance of average power to be less than 215 out of 100? So for this one, with 100, we would know that X bar would have normal distribution approximately regardless of what's the population distribution. And the mean is still 220. And the standard deviation this time will change to a smaller number because it's a sigma over square root of 100. And so standard deviation now becomes 1.6. The probability of average less than 215 now becomes, we use the p-norm and we use the 220 for the mean and 1.6 for the standard deviation. Now the probability becomes 0.00889. So it's much less than 1% of chance to observe a average out of 100 to be less than 215. Okay. Next example, look at the luggage weight. See, consider, suppose this luggage weight has a mean of 25 pounds, standard deviation of 6 pounds. And we consider a flight of 40 passengers. And we want to see, give an interval such that the average weight of their luggage will always fall into this interval. This is looking at the average weight of the luggage. We do not have the population distribution of the luggage, the weight of the luggages, but we know we have a sample size of 40. If n is equal to 40, then the average from 40 would be approximately normal. So we would know that approximately normal, the mean is equal to population mean 25, or standard deviation is sigma over square root of sample size. So once we know that, with normal empirical rule would say that 3 standard deviation around the mean will contain all of the luggage weight in there. So 3 standard deviation, and here's the mean. Mean plus minus 3 standard deviations. And after the computation, you see that the lower bound is 22.15, upper bound 27.85. So this will give us all of the possible values in this range. Summary for the properties of the sample mean. The sample mean is a random variable. When you have different samples collected and you compute the sample mean, it changes from one sample to another sample. And if you look at the distribution of these calculated sample means, these values are going to be centered at the population mean mu. And the standard deviation of those values will be equal to sigma over square root of n, where the sigma is the population standard deviation of all of the originally xi. N is the sample size. If the sample size is large, then the sample mean would be approximately normally distributed with this mean and standard deviation. But if the sample size is large, we no longer have any requirement about the population distribution. On the other hand, if the population distribution is not, if the sample size is not large, in that case, the population distribution would need to require to be normal, and the sample mean in this case would still be normal, and the mean is still mu, standard deviation is still sigma over square root of n. But this has additional requirement that the population distribution has to be normal when the n is not small. When n is small. But if n is large, regardless of n is large or small, if population distribution is normal, the sample mean would always have normal distribution. So in both situations, we can use the p norm to compute the distributions and the q norm to compute the percentiles for the calculation. And the central limit theorem for the sum will come next. And this you will see similar situation applied, except that the mean and the variance formulas will be different.